Today we're going to be discussing the fundamental theorem of calculus, and this is huge in calculus. It's more of a concept than an equation, but there's still an equation to go with it. But this will always be in every single one of your calculus classes, I promise. And this will always be on the AP exam and usually on most tests. So it's really, really crucial to understand. So what is the fundamental theorem of calculus? Well, there are two parts, and the first fundamental theorem of calculus says that if we have some function, f of x, that is defined on the closed interval and is differentiable on that closed interval, then we can say that capital F of b minus capital F of a is equal to the integral from a to b f of x d of x. Now, what does this mean? Well, capital F of x in calculus is usually used to denote the antiderivative of lowercase f of x. Now, this just means that capital F of x is sort of like the integral of f of x. So, this is our first fundamental theorem of calculus. And like I said, it is an equation, but it's more of a concept that you'll need to remember, and you won't really have to memorize this equation. So now the second fundamental theorem of calculus states that if we have some function f of x, and just say that this is the same function f of x, and it's continuous on the closed interval a to b, then it should be stated that the derivative from some a to x f of t dt is equal to f of x, where x is a variable and a is a constant. So, this is our second, and just like the first, it's not really something that you need to memorize, but it's something that you'll eventually come to understand. So let's apply what we just learned. Here's our first example problem. We're going to take the integral of 2x plus 3 dx on the interval 0 to 3. So how we're going to use this, we're going to take the antiderivative of 2x plus 3, because this is our f of x from the equation right here. So now that we're going to take the antiderivative, it's going to be x squared plus 3x, but we have to take that on the interval 0 to 3. So what does that mean? Well, it means, essentially this x squared plus 3x is now our capital F, because we took the antiderivative of f of x, and remember that capital F of x is the antiderivative, or essentially the integral of lowercase f of x. So now we're just going to plug in, if this is our f, capital F of x, then we're just going to plug in our b and our a values, and our b value is 3, and our a value is 0. So we're going to take x squared plus 3x, but replace it with 3, so replace x with 3, because that's our capital F of b, or essentially capital F of 3, minus capital F of 0, which would be, capital F of 0 would be 0 squared plus 3 times 0, because we're just replacing every x with our closed interval. So now we're going to simplify, and we get 9 plus 9 minus 0 minus 0. So our answer is 18. So the integral of 2x plus 3 dx from 0 to 3 is 18. Now here's another example problem. If we have the integral from pi over 2 to 2 pi of 2 cosine x d of x, we're going to take the antiderivative once again, because this is our f of x, and the antiderivative of cosine, remember the derivative of cosine is negative sine of x, and the derivative of sine x is positive cosine of x. So which one do we want to use here? Well, we want to use the second one, and we cannot get those confused, because if we take the antiderivative of cosine, then we would get sine. And if we take the derivative of sine, then we would get positive cosine. So now that we know the antiderivative of cosine is sine, then we're just going to keep our constant, 2, and now evaluate this on the interval pi over 2 to 2 pi. So we're going to do the same thing, 2 sine of 2 pi, because we're using capital F of b minus f of a, and our b value is 2 pi minus 2 sine of pi over 2. So what is sine of pi, or 2 pi? Well, that's 0, minus 2 sine of pi over 2 is 1. So our answer is negative 2. So first we have the derivative of the integral of f of t dt from 1 to x. So we can memorize the second fundamental theorem of calculus and know that this is just f of x. But let me show you what it means, or why that is. So as we know from the first fundamental theorem of calculus, if we take the integral from 1 to x of f of t dt, then we know that capital F, then this is equal to capital F of x minus capital F of 1. And so now we have to take the derivative of this integral, right? Because we have the derivative d over dx in front of it. So if we're going to derive capital F of x, well, remember that f of x, or capital F of x, is just the integral of f of x. So if we take the derivative of this, if we take the derivative of the integral, then the integral is just gone. So the derivative of capital F of x is just lowercase f of x. But what about capital F of 1? Why did that just become 0? Because there's nothing here. Well, we know that capital F of 1 has to be a constant, right? Because once we take the integral of a function and then we plug in a number into every single x variable, then we're not going to have any variables left, and that leaves us with a constant. So we know that capital F of 1 is just a constant, and what do you get when you take the derivative of a constant? You get 0. So that's why this is just f of x. So let's do it again. I know it's really tedious, but it's the same thing. If we're going to take the derivative of f of x d of x from the interval negative 2 to a, then we're just going to be left with f of a. You know, saying that f of the a is actually a variable and not a